you see my screen?
Yep.
Yes. Yep.
So I again uploaded Jupyter notebook file and the PDF file for today's session. So if you have not downloaded in previous session, then please download. Okay, so previous session we discussed some notations that we will use in machine learning, and today we will see how can we train a linear regression model, right? So linear regression or regression problem we have already seen. In regression, what we do for given input, our output is a real valued, right? So for given input, our job is to predict a real valued output, right? Now, depending upon what type of problem we are solving, we can have a single output or we can have a multi-output problem, right? So in single output, we will predict a single value, single real valued we will predict. In multi-output problem, we will predict a output vector, a vector of real values we will predict in output, right? Okay, so here first we will see how can we predict a real valued number or output for the given input. Now again in input we can have a single input, we can have multiple input. Single input means in input we can have one feature or we can have multi-feature input where we are having multiple features in input, right? So for example, in house prediction problem, there we will have multiple inputs, right? Or we will have multiple features, right? Okay. So linear regression, as I said, goal is to predict a real valued output given input, given input feature, right? So here we are going to predict life satisfaction given GDP per capita. So this GDP per capita is here our input and life satisfaction is output. And as you can see here, we are what exactly we are doing? We are here trying to estimate a relationship between input and output, right? We are here trying to estimate relationship between input and output, and using that relationship, given some input, we will predict a real valued output, right? So since here we are we are using a linear regression model, so here we will fit a line depending on our input. So for example, if we only have one feature in our input, then in regression model we will predict a line, right? Suppose if we have two features, so for example, on x-axis we are having one feature value, y-axis we are having one feature value, then we will predict a plane, right? If we are having more than two features, then we will estimate a hyperplane, right? So again, this line, plane, or hyperplane all are the linear models, right? So that's why these methods are called linear regression, because here we are learning a linear model, right? Linear can be plane, can be line, can be hyperplane, right? Okay. So since here we are only having one feature value, or in other words, we are only having one input, so therefore here we will predict a line, right? Now for the given input value, our goal is to predict the output, right? So we are given the actual output, the ground truth or the actual value we already know, and we also predict output using using the model, right? So we will use model to predict these values, but actual ground truth values we already know, right? And for the future time, we only know the input and our goal is to predict the output, right? So since input output pair is given, so therefore this regression is a supervised learning problem, right? Because in supervised, what we do, we have input output pairs and we will use input output pairs to solve our problem. And in regression also, we will use this input output pair. So therefore regression is a supervised learning problem, right? Okay. So since here we are using a linear regression, so and here we are only having one feature, so we will use a line. And what is the equation of line? Y is equal to mx plus c, right? So this equation looks like a equation of a line where this life satisfaction you can think like y, life satisfaction y, GDP per criteria X, theta 1 M, and theta 0 C. So Y is equal to MX plus C, right? Or you can think here we are using two unknowns, theta 0 and theta 1. GDP per capita we already know, and our goal is to estimate life satisfaction. So this is unknown that we want to estimate using machine learning model. Theta 0 and theta 1 are the parameters of that machine learning model or unknowns that we will estimate here. While learning this machine learning model, we will estimate these unknown theta 0, theta 1. GDP per capita is here our in or feature value, right? Okay. Now here, if you change this theta 1, if you change the value of theta 1, the orientation of line will change, right? Because theta 1 here is nothing but the slope. So if you change this slope value, the orientation of line will change. If you change this theta 0 value, the shifting will change. Shifting from origin will change, right? So for example, let's say if you decrease this value of theta 0, this line will shift towards origin. If you increase this value, this line will shift away from origin, right? So if you change this theta 0 value, the shifting will happen. If you change this theta 1 value, the orientation, the angle of this line will get changed. Now, by shifting appropriate line, or by tuning this orientation, we will fit a line, right? Because let's say for giving this data point, if we want to fit a line, then how can we fit a line? By changing two parameters, two unknown values, orientation and shifting, right? Which is nothing but the this theta 1, theta 0 is called also called the intercept value, right? So if you change the shifting, if you change the orientation, you can fit a appropriate line for this given data, right? Okay. And this theta 0 and theta 1, these two unknown values that I'm writing here are the optimal value for this machine learning model, right? So our goal is to find optimal value of theta 0, theta 1 such that model is best possible for this given data, right? Okay. Yeah, so I have already discussed the slide. So as I said, theta 0, theta 1 are the unknowns, and these unknowns are called the model parameters, right? And in machine learning models, our goal is to learn optimal value of these unknown parameters, theta 0, theta 1, right? GDP per capita is input feature value, life satisfaction is output, right? Yes, so this equation means we are learning a linear model, right? Yes. Now for the given input, for the given value of input, we will use this machine learning model. We will use optimal value of theta 0, theta 1, and we will simply plug in here the value of input, and model will give us the output value, real valued output value, lab satisfaction it will give, right? So for example, for the given value of 33,000, if you plug in here GDP per capita 33,000, if you plug in here optimal value of theta 0, theta 1, using this model, you can get the output value, life underscore satisfaction, life satisfaction you can estimate, right? Okay, so any doubt here? Okay. Now suppose let's say if you are having n number of features, now in that case, can you tell me the linear model? What type of linear model we will learn if we are having n features or n inputs? So here we are only having one input, right? What if we have the n input? So suppose if we have n number of input x1, x2 up to xn, right? Or let me simplify this problem. Suppose we have the uh, yes, suppose we have the 3 input, right? Then what will be the equation of line in that case? Or since we have the 3 inputs, so we will learn here hyperplane, right? Then can you tell me the equation of plane or
It
hyperplane in
would,
this case?
yeah, it
Yes,
would be theta 0 plus theta 1 into x1
yes, yes. So in this
plus
case,
theta 2 to
yes, yes, the output will be theta 0 plus theta 1 time x1 plus theta 2 time x2 plus theta 3 time x3. So this will be the linear model, right? Now here, what are my unknowns? Theta 0, theta 1, theta 2, theta 3. So these values are the unknown, and x1, x2, x3 are the uh, input feature values, right? Or you can say inputs, right? X1 is first input, second input, third input, right? Or you can think feature, X1 is the first feature, second feature, third feature, right? Like that. Okay. So you will learn this type of model when we have 3 inputs. Similarly, if we have n inputs, you will extend these equations, right? Theta 4, x4 plus theta 5, x5, and so on, right? Okay. So this linear model, I can also write uh, theta transpose x. I can write this equation in vector form, in matrix form, matrix vector notation I can write here, right? Uh, so in this notation, I'm using either matrices or vectors, right? So here this theta is again a vector, x is a vector, right? So by default, when I say vector, vector means I am saying column vector, right? So by default, we will assume all vectors are here in this course. We are referring to a column vector, right? So when I say x is a vector, which means x is a column vector, x1, x2, x3, right? So this is the input feature vector that we have originally, right?
that would be capital X, right?
No, no, no. In capital X, we will use matrices, right? So here I'm using uh, small x in bold font, right? Yes.
Sorry, what will be difference between capital X and
So capital X
uh,
we generally use for the matrices as per our notation, and small x we will use for vectors, right? Okay. Yes. So here in yes. So we will use capital X for matrices. We will use lowercase bold font for vectors, right?
okay, okay.
And this ith superscript is nothing for the ith input, right? So for example, for a first input here we will use x1, second input we will use x2, right? Yes. So since we are having 3 input x1, x2, x3, so these are the values of features, right? So in input we are having 3 features x1, x2, x3. So feature vector x here will be okay. So x is a vector, column vector x1, x2, x3, right? And this theta is again a vector. So theta will be a vector of size theta 0, theta 1, theta 2, theta 3, right? So the size of this theta vector will be 4 cross 1 and the input vector is 3 cross 1, right? So we cannot perform this dot product, right? Theta transpose x, because this, if theta is a column vector, what will be the theta transpose? Theta transpose will be a row vector. Theta 0, theta 1, theta 2 and theta 3. So size will be 1 cross 4, right? So if you transpose column vector, you will get a row vector, right? And here what we are doing, we are doing a dot product between theta and x, where theta is a vector, x is a vector, right? Yes. So if you want to get the same equations here, what you can assume, here we are having 1, right? You can write something like this: theta 0 multiplied by 1 plus theta 1 time x1, theta 2 time x2 plus theta 3 time x3, right? So if you use this notation, what I can use here, I can here append 1, right? So that I can perform the dot product between theta and x, right? Because here the problem is the size of this theta is 1 more than the size of input vector x, right? Because we are only having 3 inputs, right? First feature x1, second feature x2, third feature x3. So in original input vector, we are only having 3 values, 3 input features we are having, 3 elements we are having. But in unknown vector, we are having 4 elements. Why we are having here one more extra element? Because of this bias term theta 0, right? So this theta 0 is a bias term, and this theta 0, using this theta 0, we can control the shifting of line, right? If you change the theta 0 value, the shifting will change, right? Okay. So how can we solve? How can we fix this problem? So here, what we will do? We will create a new feature vector x new, and this x new will be nothing but the 1, x1, x2, and x3. Now the size of this x new will be 4 cross 1, right? So here we will use x new, right? And x new and x, what is the difference? Here we are just adding here one more element, and that element will always be 1, right? Because you can also write the same equation like theta 0 into 1 plus theta 1 x1, theta 2 x2, theta 3 x3. So this one element here we are adding extra, right? Okay. Now what exactly we are doing here? We are performing a dot product between theta and x new, right? If you perform dot product between uh, theta and x new, what value you will get? Theta transpose x new, right? And you will get the same value, right? If you use, if you write here theta transpose, what is my theta transpose? Theta 0, theta 1, theta 2, theta 3, and this x new is nothing but this vector. So I will write here 1, x1, x2, x3. If you perform these two vector multiplications, right? The size of this vector is 1 cross 4. Here you have size 4 cross 1. So in output, I will get the single value, right? I will get the single one element, right? Because I'm doing here multiplication between 1 cross 4 and 4 cross 1. So what I will get in output? Theta 0 into 1 plus theta 1 x1, theta 2 x2, theta 3 x3. So I will get the same output here, right? So this model I can also write in several forms. I can write here theta transpose x new. I can also write model is nothing but the dot product between theta and x new, right? Any doubt here? Right.
No.
So here in this notation, we have to change this feature value. We have to add one more extra feature, and that extra feature is nothing but the constant value 1, right? To accommodate this bias term theta 0, right? Okay, so here what is model parameter here? This vector theta. This vector theta is the unknown vector that I am trying to here estimate, right? So this theta is a unknown vector, or model parameters here are the this vector theta, and this vector theta contains uh, multiple unknowns, right? Because it's a vector, so it can have multiple unknown values, right? So for example, in this case, this theta contains 4 unknown values: theta 0, theta 1, theta 2, theta 4. Sorry, theta 3, right? So theta 0, theta 1, theta 2, theta 3, here are the 4 unknowns for this model, linear model, right? So whenever I say linear model, what I mean by linear model, theta transpose into input, and you will get output, right? And if we have this bias term, then we will add constant value here. If we don't have this bias term, then we will not add here any extra value, right? Suppose in our model we don't have bias term theta 0, then we will not add here this value 1, right? Here why are we adding this value 1? To accommodate this bias term, right? So any doubt here? Okay. Now let's say if you yes, any doubt?
No.
Okay. Now let's say if you want to learn a non-linear model, so let's say non-linear model of degree 2, then can you tell me the equation of model equations that we will use here if you wish to learn a 2-degree polynomial? So here linear model means what degree we are what is the model degree here? 1, right? 1-degree model we are learning. So since we are having 3 features x1, x2, x3, so as you can see here, in each term either we can have degree 1 term. So for example, this degree 1 term, degree 1 term, degree 1 term, because here degree of x3 is 1, degree of x2 is 1, degree of x1 is 1. So in degree 1 model, either we can have a degree 1 term or we can have degree 0 term, right? So all degree 1 and degree 0 term will be there in degree 1 polynomial. Similarly, degree 2 polynomial, we will have all degree 2 term, degree 1 term, and degree 0 term, right? Now suppose if we have two inputs x1 and x2, and now we are learning a non-linear model. So as I said, for non-linear model output, so again output will be a real valued output, theta 0 bias term plus, since we are using degree 2 polynomial, so in degree 2 polynomial there will be degree 2 term, degree 2 term, degree 1 term, and degree 0 term. So this bias is nothing but a degree 0 term, right? Because here degree is 0, right? Then we will have degree 1 term. So since we are having two variables, so degree the number of combination will be here 2, theta 1 x1 plus theta 2 x2. Then we will use degree 2 term, right? So degree 2 term will be, let's say, theta 3 x1 square plus theta 4 x2 square plus theta 5 x1 x2, right? So this type of model we will learn if we learn a degree 2 polynomial, where we are having two feature value x1, x2, right? So as you can see here, we are having term with degree 2. So for example, this is a degree 2 term, degree 2 term, again degree 2, right? So 1 degree we have will have for x1, 1 degree we will have for x2. So 1 plus 1, 2, right? Degree 2 term. Then we will have degree 1 term, degree degree 0 term, right? In degree 3 polynomial, we will have degree 3 term plus degree 2 term plus degree 1 term plus degree 0 term, right? Okay, so since here we are learning a linear model, so here we will have either we will have degree 0 term plus degree 1 term, right? Okay, yes. So this slide I have already covered. So test time, what we will do, we will use optimal values of unknown parameters, and we will use input values, and we will predict output value, right? Okay, so here this y is equal to mx plus c is nothing but a line. I have already discussed this slide. So this c is nothing but the bias term, right? So this c here is a intercept value, right? And if you change this c value, the shifting of this line will change. So suppose, let's say, if you fix this m value, if you fix this slope, and let's say if you decrease this c value, if you decrease this c value, the line will shift in this direction, right? This direction line will shift if you see decrease c value. If you increase c value, this line will shift along this positive y direction, right? If you decrease c value, the line will shift along negative y direction. If you increase c value, this line will shift along positive y direction. Now, if you change this m value, if you change this orientation value m, the orientation of this line will get changed, right? You can rotate this line by changing m value, right? Okay. Now, what if this intercept value theta 0 is 0? So suppose if this intercept value theta or c value is 0, then this line will pass through this origin, right? If in this equation the c value is 0 or theta 0 value is 0, bias term is 0, then this line will always pass through origin, right? Likewise, let's say if we do not have bias term in a linear model, then the line or plane or the hyperplane will always pass through the origin, right? So intercept is 0, then line will pass through origin. If intercept is 0, and if we are learning a model where we are having two feature, then that plane will pass through the origin. So line or plane or hyperplane will pass through the origin if we don't have bias term in our model, right? Okay, so let's say if we do not have any bias term, then we may not be able to fit a model for the given data, right? Because here we have put one restriction that model must pass through the origin, right? So here we can only change the orientation. We cannot shift this line, and we can only change the orientation, right? So in that case, we may fit a model. So depending upon data, we may fit a model, we may not fit a model. So for example, if you are given data points, let's say for these data points, you are learning a linear model, right? And if we are not using bias term in our model, then we can only change the orientation. So we cannot fit a model for these points, for these given points, right? Because for that we need to shift this line. So therefore we must have a bias term in our model, right? Without using bias term, we cannot fit a model, right? So this type of model can only possible when we have bias term, because we have to shift this line, then only we can fit a model, right? So this is the importance of bias term, right? If we do not have a bias term, then uh, it may possible that we cannot fit a good model, good linear model for the given data, as you can see in this example, right? Because sometimes we need to shift this model to fit a model for the given data points, right? Okay. Okay, now let's go back to end-to-end project where we are predicting a house price for the given input features, or for the given input values. We are predicting a real valued output house price. What are the input that we have for the house price prediction problem? Longitude, latitude, right? Median income. So these are the input values or input features, and our goal is to predict the real valued house price, right? So again, if you want to here use the linear model, we will use a degree 1 term and degree 0 term, right? Because here we are learning a linear model. So in linear model, we will have degree 1 term and degree 0 term. So this equation I have already discussed, right? So since now we are having 4 features, first, second, third, and fourth. So therefore, we will use theta 0 plus theta 1 times first feature, theta 2 times second feature, theta 3 times third feature, theta 4 times fourth feature, right? So we will use this type of model if we want to learn a linear model to predict house price for given these 4 feature values, right? Okay, so these equations I have already used, right? Again, here if you want to learn a non-linear model, let's say non-linear model of degree 3, then we will have term like degree 3 terms, degree 2 terms, degree 1 term, and degree 0 term, right? Degree 0 terms means the biased. So here this theta 0 is the degree 0 term or biased term. Yes, so this equation I have already explained, right? If we have n feature values, x1, x2, xn, and if we learn a linear model, the equation will be something like this, right? Okay, so here this theta j means the jth model parameter, right? Theta 1 means first model parameters, and theta 0 means the bias constant, bias term, right? And this theta vector, can you tell me here the size of unknown vector theta?
n+1.
Yes, n plus 1. So the size will be n plus 1 cross 1. There will be n plus 1 rows and 1 column in unknown vector theta, right? Because here we will have one more extra term, one more extra unknown because of this bias term, right? Theta 0. Okay, so here our goal is to predict these theta vector, these unknown values, theta 0, theta 1, theta 2, theta n. And input we already know. X1 value we know, x2 value we know, xn value we know. And our goal is to predict this output y, right? And here, how many features we are using? N features we are using. So x1 is the first feature, second feature, nth feature, right? So here we are using n number of feature, x1, x2, xn. And unknowns here are the n plus 1, theta 0, theta 1, theta 2, up to theta n. And these unknowns are nothing but the model parameters that we will learn. So here our goal is to estimate the optimal values of these unknowns. Yeah, so this slide I have already discussed, right? If we do not have the bias term, then sometimes it is not possible to fit a model for the given data. So depending upon uh, our need and the data points, we we may have bias term or we may not have bias term in our model, right? So for example, uh, uh, if let's say if model passes through origin and the and it is also fitting the models, it is also fitting the all data points that we have in our data set, then there we will not any bias term, right? So what we will do, practically we will always add a bias term, and if this bias term is not required, then while learning the values of these unknowns, this theta 0 value will be 0 or close to 0, right? So we will always add bias term theta 0. If this bias term is not required, then in that case the value of this theta 0 will be either 0 or very close to 0, right? Okay. Yes. So theta, as I said, is nothing but a unknown vector, and theta transpose will be a row vector, right? Okay, so here I think theta 0 is missing, so theta 0 must be there, right? Theta 0, comma theta 1, comma theta 2, and up to theta n, right? Because we always use bias term, right? Okay, and in here in input, we are adding here one more extra term, constant term, and that constant term is 1, right? So that we can accommodate this bias term, right? Because here we are doing a dot product between two vectors, theta and x. X is a vector, input vector, theta is a vector, unknown vector, right? The size of this theta vector will be n plus 1. Original input vector size will be n. And since we can only perform dot product between two same size vector, right? So therefore, to perform this dot product, we will add one more term in input vector, and that term will be a constant 1, right? That I have already discussed, right? Okay, so here this H is called hypothesis, and this H theta we are using for the model theta, right? So yes, so this slide I have already explained, right? To perform this dot product theta and x, how can we perform this dot product? When we add one more term here in input vector, and that term is a constant 1, right? So we will add one more term here, and then now we have uh, two n plus 1 size vector, because the size of this theta vector is also n plus 1, size of input vector is also n plus 1 after adding this constant term 1, and we can easily perform dot product between two n plus 1 size vectors, right? Okay. Yes, and this h is a hypothesis function, and using this model parameter theta, this h function or hypothesis function fit model, and it will estimate optimal value of thetas, and using optimal value of theta values, we can predict output value y, right? So this theta is unknown. We will learn optimal value of theta. Input vectors we already know. We will plug in this input vector here in these equations, and we will predict output value y, right? So this h theta is the function, and this function here in is called the hypothesis function, and this function is nothing but the theta transpose x, and this function depends on, this function is taking x as an input, and the parameter of this function is theta, right? So h theta x means h is a function, and this function takes x as an input, and theta is the parameter of this function h, right? And this what is the form of this function? Form of this function is theta transpose x, right? Okay, so now the question is, how can we calculate the optimal values of unknown vector theta? Optimal values of these parameters, uh, theta, theta 0, theta 1 up to theta n, right? So for that, what we will do, we will train our model using training data. So using training data, we will train our model, and we will estimate optimal values of these unknowns theta, right? These theta values, theta 0, theta 1, theta n, right? Okay, so for that, we will first define a loss function, right? So training a model means we are estimating model parameters. We are estimating unknowns. We are estimating theta values, right? So that model best fit the training data. And for that, we need a measure of how well or how poorly model fits the training data. And to measure how well or how poorly the model fits the training data, we will use some metric. And in this case, the metric can be the squared error, can be the absolute error, right? So for that, to solve the regression problem, you can either use the root mean square error or you can use the mean square error. In both case, you will get the same answer, or even you can also use the absolute error, right? Okay, so this error, square error or root mean square error, why are we using this performance matrix? Or this matrix, why are we using? Because we want to calculate how well or how poorly the model fits the training data, and this thing we can only check when we have some measure, right? And here what measure we are using, mean square error, or you can also use the absolute error, right? Okay, so we will use mean square error for training the model in this session. But you can also use the absolute error. In fact, we can have several types of error, right? But for the sake of simplicity, I'm using here the squared error, right? But it's not like that for regression problem. You can only use the squared error. Or you can use absolute error, and in fact, several other types of error also there, right? That you can use. Okay, so now, if you want to use the square error, you have two options. Either you can use the root mean square error, or you can use the mean square error. But even if you use the RMSE or MSE, you will get the same solution, right? So solution will not change, right? But yes, if you are using MSE, that then it is simpler to minimize MSE than RMSE, because in RMSE we have to perform one more step, square root, right? Because RMSE is the root mean square error and MSE is the mean square error. So if you calculated MSE, then we have to perform square root, then we can get the RMSE, right? So it is better to minimize MSE rather than RMSE, because in RMSE we have to perform one more step, square root, right? And if you minimize MSE or RMSE, it doesn't matter, you will get the same solution, right? So this MSE or RMSE is the error, right? And what we want? We want high error or we want low error?
Low.
Yes, so we want low error, right? So suppose this MSE is the error E and RMSE is a square root of E. So let's say here, let's say if I'm saying that error has to be as low as possible. So if E is low, then square root of E is will also be low. Or in other word, if square root of E is low, then E is also low in that case, right? So either I can use E or I can use square root of E. In both cases, I will get the same solution, right? Because it is not possible that E is the lowest and square root E is not the low value, right? Whenever this E is low, square root of E will also be the lowest, right? So therefore, either I can use E or I can use square root of E. I will always get the same solution, right? So therefore, it doesn't matter. You can use MSE or RMSE. In both case, you will get the same solution, right? Okay, so MSE we have already covered. So very quickly, I will cover here. So again, I'm using I'm taking regression problem, and in that linear regression problem, we only have one feature value, right? So one feature value means univariate linear regression. When we have multiple features, that then that linear regression is called multivariate linear regression problem. In multivariate, we will have more than one features. In univariate linear regression, we will only have one feature value. So suppose we only have house area and we are predicting house value. So given house area value, our goal is to predict output house value, right? So this problem is a regression problem, and here we are learning a linear model. And since we only have one feature value here, house area, so therefore this problem is called the univariate linear regression, right? But this problem is a multivariate linear regression, right? Multivariate linear regression, because here in input we are having more than one feature value, right? X1, X2, Xn. Yes. So again, here we will fit a one line and we will estimate two values, W0, W1. So either you can use here theta 0, theta 1, or you can use W0, W1, right? It doesn't matter. These are the unknowns, right? W0 is a bias term, W1 is a orientation term, slope term. If you change W1, orientation will get changed. If you change W0, the shifting will get changed, right? Okay. So now, if you want to measure how well or how good we are fitting this line for the given data points, we need to have some measure of that, right? So for that, we will use error, right? So suppose, let's say, if you say this is the best model, this is the best model for these data points, then how can we say that this is the best model? When we have some notion of some measurement using which we can say this is the minimum, or that quantity is maximum, and on the basis of that quantity I'm saying this is the best model, right? So here to say that this is the best model, I'm using error. I'm using here error, right? So error means these are the 5 training data points, right? First training data point, second training, third, fourth, fifth. This y1 is the actual value, actual output, and this y1 hat is the predicted value for this input one, right? Okay. So for this input value x1, we are having two values. Y1 is the actual output, and this is the model predicted output y1 hat, right? Similarly, for the second input, we will have model predicted output and the uh, actual output, right? Y2 hat and Y2. So we can calculate here the error, the difference between the actual values and the predicted value. Now this difference can be positive, can be negative. So if you are defining uh, uh, actual minus predicted, right? Actual minus predicted, then this difference will be positive and this difference will be negative, right? Because here error we are defining like actual minus predicted, right? So actual values is higher, predicted values is lower. So therefore, this difference here is positive, the difference is negative. If you are defining error is equal to predicted minus actual, then the sign will get changed, but sign will doesn't matter. We, we, we will not care about this sign, right? So what I mean here, error can be positive, can be negative, right? Depending on whether you are defining error is equal to actual minus predicted or predicted minus error, it doesn't matter. We are getting here some error we are getting. That error can be positive, can be negative, which means this model is not perfect, right? Because we are having some error, right? Okay. Now this error can be positive, this error can be negative, right? So what ideally we want lowest error, right? Okay. So suppose here I'm using error, for error I'm using predicted values minus actual value. So if I use predicted values minus actual value, then uh, this error will be negative and this error will be positive, right? Okay. So for some data points, I will get positive error. For some data points, I will get negative errors, and positive will and negative will get cancel out, right? And to avoid this case, what I will do, I will here use the square, right? Square error. so that error will not get cancelled out, right? Because as you can see in this example, some errors are positive, negative. So if you directly sum these errors, some errors will get cancel out, right? Positive error will cancel negative error, negative will cancel positive error, and you may end up getting a low error, but in fact in reality you are having a your model is making a huge error, right? Now to avoid this case, we will use here the squared error, so that each and every error will get contributed to the final measurement, right? So here we are measuring the square error, right? So if you measure the square error, now this positive error will also added, this negative error will also added in the final value, right? Okay, so we will take square error, and then we will calculate this mean value, average square error we will calculate, right? So yi hat minus yi is nothing but the error for ith input, and we are squaring this term, and then we are doing this summation, and then uh, finally we are taking this averaging, right? So it's a average squared error, or in other word, it is the mean square error, right? Here, what is this m is the number of training data points. So suppose here if we have the 5 data points in this case, so therefore here the value of m will be 5, right? So small m is the number of data points. Okay. Now, what we want? We want this mean square error to be as low as possible. So for the best model, this value mean square error will be as low as possible, right? So we have to train a model that result in lowest mean square error, right? Okay. So we have to estimate unknown parameters theta. We will use error matrix mean square error, and model will try to estimate these unknown values in such a way that results in lowest possible mean square error, right? So for example, here training method will try to estimate in such a way this mean square error is as low as possible for these given 5 data points, right? Okay. Yes. So simply I'm plugging y hat value, right? Because yi is the actual value for the ith input. Yi is the actual value for the ith input. Yi had the model predicted value for the ith input. So if I replace the value of yi from these equations, then I will get this equations, right? Again, MAC is nothing but the mean square error is nothing but the predicted value minus actual value, and then we are doing this square term, summing it, and then we are taking averaging, right? So it's a mean square error where this first term is nothing but the predicted value, model predicted value, right? Because theta transpose x is the model predicted value minus this yi is the actual value, right? And since we are having m many data points, so we will sum this error I is equal to 1 to m, and then we will do this averaging, right? Because it's a mean square error. So using this error, MAC error, we will estimate the best possible model. And best possible model means the unknown vector theta that results in the lowest possible MAC error, right? Okay. So again, here in this equation, xi is the ith input. right? Xi is the ith input, theta is a unknown vector, yi is the output label for ith input, right? So let's take an example. So let's say for the house price prediction problem, we are having several values: latitude, longitude, then median income, median house value, right? So if we are predicting median house value, then this value is the actual output. So here y1 is the, so here 1 means we are saying it is the first example, first training data points, right? So superscript 1 means first example. So here we are using superscript I means it is the ith training example, and it is the ith actual output, actual output for the ith training example, right? So yi means I for the ith input, it is the actual output, right? Xi means input for the ith input. Sorry, for the ith in data points, this is the input vector xi, and yi means output vector, actual output for the ith input, right? So since here we are this is the first data point, these values are for the first data points. So in superscript we are using 1, right? Okay, so if you want to predict the median house value, this is the output value. And what are the input values here? This value is the input, or first feature, second feature, third feature, and fourth feature. So we will have a vector of size 4 cross 1. We will have one output, and we will use machine learning model to predict output value for given this input vector x, right? So we will use theta transpose xi to calculate the predicted value. Then we will have the actual value. We will use this error matrix MAC to calculate the total error, right? Any doubt in this slide? Okay, so this slide I have already covered, right? Our goal is to find the optimal value of theta that minimizes the this error, RMSE error. So we want as low as possible MAC, and for that we will learn optimal value of theta vector, right? Okay, now if you want to minimize this MAC, there are two methods to minimize MAC. First method is the closed form equation, or you can use the normal equation to minimize MAC. The second method is the gradient descent, right? So gradient descent is the iterative method, iterative approach, and the normal equation is the equation using which directly you can get the solution, right? So there are two ways to minimize this loss MAC. One way is to use one mathematical equation that directly using which you can get the answer, directly using which you can get this theta value, unknown vector theta. The second is the iterative method, and gradient descent iterative method. Using this iterative method, you will use several iterations to reach the solution, right? Okay, so first we will see normal equation method, and then we will see gradient descent method, right? And what exactly here we are doing? We want to minimize MAC loss, we want to minimize error, and we want to estimate the unknown vector theta that minimizes this error, right? If you change this vector theta, error will get changed, right? So we want optimal theta that results in lowest possible MAC error, right? Okay, so first we will see normal equation method. Hello, am I audible?
Yes.
Yes,
Yes.
sir.
Okay, okay, okay. So I think this you already know from calculus. So suppose if you want to calculate minimum values or maximum values for any given function, what we will use? We will use the derivative. We will differentiate this function with respect to x, and we will use this differentiation f dash x to calculate minimum or maximum values, right? So as you can see here in this example, uh, for we are having several minimum values and several maximum values, right? So, so for example, this is the minimum value, maximum value, again local minima, local maxima, global minima, global maxima, right? So the important point that you can note here, for all these minima and maxima points, derivative is zero, slope is zero. If you calculate tangent for this point, the slope will be zero, right? Similarly, for this maxima point, if you draw tangent, the slope will be zero, right? So you can use this fact uh, to calculate the uh, solution, right? So as you can see here, if you draw tangent, the direction of tangent will be parallel to x-axis, right? Which means slope of this tangent is zero, right? For all these maxima minima points, right? So if you want to optimize something, optimize means if you want to maximize something, if you want to minimize something, there can be several methods. So one method is you can use first order optimality. First order optimality means you will use first order derivative, f dash x you will use, right? You will differentiate that function and you will set it to zero and you will get your solution, right? So let's say if you want to, so this is the loss function. Suppose this is the loss function, and you want to get the optimal value of parameters. And if you are using first order optimality, this method, what this method will do, it will differentiate this function with respect to unknown parameter. And since here for this optimal value, the slope will be zero. So what you will do, you will set this differentiation is equal to zero, right? Because the slope is zero, gradient is zero. So this gradient has to be zero, right? So you will use this fact gradient is equal to zero, and you will calculate uh, the values of this unknown parameter theta, right? Likewise, let's say if you are minimizing or maximizing this type of function, again you will use same fact gradient has to be zero for minimum and maximum value. So you will calculate gradient, you will differentiate this function with respect to unknown, set it to zero, and you will solve this equation to get the unknown parameters theta, right?
What is this notation L?
L means loss function. So L can be MAC, L can be RMAC, N can be mean absolute error, or it can be any loss function, right? So this curve here is the loss curve, right? You can think on the horizontal axis we are having unknown value theta, vertical axis y-axis we are having loss, and loss can be absolute loss, can be scared loss, mean scared loss, right? So since we want to minimize loss function, so therefore you can use this fact that derivative or gradient is zero when we have the lowest loss or the highest loss, right? Because for both maxima and minima, gradient must be equal to zero, right? Gradient means this derivative. Okay, so in normal equation, we will use first order optimality, right? So what exactly we will do here? We will use this equation MAC. We will different. So here in this equation, what are unknown values? Theta. Theta is the unknown value. So again, we will differentiate this equation with respect to theta, set it to 0, and then solve for theta. So if you differentiate this equation with respect to theta and set it to 0 and solve for unknown theta, you will get this equation, right? And here, since you are getting a closed form solution means we are getting here a formula using which directly we can calculate unknown theta, right? So so that's why this solution is called the closed form solution. And how are we getting the solution? We are getting the solution. So you can use this equation MAC, this loss equation. Since we want to minimize this equation, so what we will do, we will differentiate this equation with respect to unknown theta, set it to 0, and we will get the solution theta, right? So this is how you can derive this equation theta, right? And directly you can get the solution theta, because here theta is the unknown, right? What is this X? Capital X. Capital X is nothing but the matrix where first row means first data points, second data points, second row means second data points, and so on, nth data points, right? So first row means first data points, second row is the second data points, right? Nth row is the nth data points, and column means feature. So for example, first column is the first feature value, second column is the second feature value, likewise, right? So solution vector theta, or this unknown vector theta, is nothing but the X transpose X inverse X transpose Y, right? Where this X is a input matrix, Y is a output vector, right? Okay, let's take one example. Suppose we are having m data points, right? And there are n features. So number of features are n, and number of data points are m. And suppose we are having bias term in theta 0. Now, can you tell me the dimension of shape of X and Y and this theta vector? So since here we are having n number of feature, so what feature values we will have in our input? X1, X2 up to Xn, right? So if we are learning a linear model, what will be my unknown values? Theta 0, theta 1, theta 2, and theta n, right? And model will be output is equal to theta 0 plus theta 1 x1, theta 2 x2, and so on, theta n xn, right? So there are n features, and number of unknowns will be n plus 1. So size of this theta vector will be theta, size of theta will be theta 0, theta 1, theta n. So size will be n plus 1 cross 1. There will be n plus 1 rows and 1 column, right? Now, can you tell me the size of X? Because here I'm arranging inputs row wise in this matrix X, right? But since we have one more extra term, bias theta 0, so therefore we also have to accommodate So here I will add extra row or I will add extra column to accommodate this bias term theta 0. Right? Directly I cannot use this x, right? Because we have one more extra term theta 0. So we have to add one more feature to our data, right? Because as you can see here, we are having n features and we are having n plus 1 unknown. So we have to add one more feature 1 so that we can accommodate theta 0, right? So for that, should I add here one column or one row column or row I will add here? So in each input, I will add one, right? So can you answer this question? So I have to add.
Oh,
Yes. Hello, am I audible?
Yes, sir.
Yes, yes. So should I add here one extra column or extra row? One column.
Extra column.
Yes, extra column I will add here, right? So that extra column is nothing but the vector of ones, all ones, right? Because this row is my input, right? First row means first input, second row second input, right? So in each input I will add value 1, right? So suppose here I am having x 1 1, then x sorry, yes, second feature of first input, then another feature of first input, right? So earlier what I have here, x11 first feature of first input, second feature of second input, and so on, nth feature of first input, right? So since I have to add one value here, so now my input will become like this, right? Similarly, the second row will be 1, then first feature of second input, second feature of second input, and so on, nth feature of second input, right? So likewise, if I am having m number of data points, so last row will be x m1, first feature of mth input, second feature of mth input, and so on, nth feature of mth input, right? So this will be my row. So now the size of, I think I'm having some problem with my internet. So can you hear me?
Yes, sir.
Okay, okay, okay. So now can you tell me the size of x? What will be the size of x? Size of x will be n plus 1, n plus 1. So size of x will be n plus 1 because there are, uh, sorry, it will be m cross n plus 1, right? Because there are m number of rows, right? Because we are having m number of inputs. So for each input, we will have one row, right? So for each input, we will have one row. And since we are having m number of inputs, so therefore number of rows will be m into number of columns. So originally we are having n features, so there will be n columns. But to accommodate bias term, we are adding one more extra column, 1. So therefore, here now the number of columns will be n plus 1. Right. So this extra column we are adding here to accommodate bias term. Right. So what is this extra column? Columns of all ones. Columns of all ones we are adding here to accommodate this theta. Right. Okay. So this the size of this theta will be n plus 1 cross 1. Right. Size of x is nothing but the m cross n plus 1. Now can you tell me the size of output vector y? What is this y? Output for each input, right? So its size will be, so what we will have here in y vector, output for first input, output for second input, output for third input, and so on, output for mth input, because we are having total m points, right? So here we will have output for first input y1, y2, and so on, ym. So the size will be m cross 1, right? Because there are m number of data points in our training data, right? So this is nothing but the output for first point y1, y2 is the output for second point, ym is the output for mth data point, right? Ym. So size will be m plus 1. Okay, so can you put these sizes and can you verify finally we are getting n plus 1 cross 1? Okay, so size of x is m cross n plus 1. So what will be the size of x transpose? Size of x transpose will be n plus 1 cross m, right? If size of x is m cross n plus 1, size of x transpose will be n plus 1 cross m. Then we will have this x. So we will have m cross n plus 1. So if you multiply these two matrices, what finally we will get? N plus 1 cross m multiplication with m cross n plus 1. Finally, we will get n plus 1 cross n plus 1, right? So here, if you multiply these two matrices, you will get n plus 1 cross n plus 1, right? Then we will have x transpose. What is this x transpose? Size of x transpose is nothing but the n plus 1 cross m. N plus 1 cross m. So if you multiply these two vectors, n plus 1 cross n plus 1 into n plus 1 cross m, what size finally I will get? N plus 1 cross m, right? So after doing this multiplication, I will get a matrix of size n plus 1 cross m, right? Now, size of this matrix is n plus 1 cross m. Size of y is m cross 1. So if you multiply these two matrices, what finally I will get? N plus 1 cross 1. N plus 1 cross 1 is the size of output. And you can verify here the size of theta is also n plus 1 cross 1. So after performing these multiplications, you will get output vector theta of size n plus 1 cross 1, right? Any doubt in this equation? So as you can see here, directly we will get your answer, right? We will arrange input row wise and we will use X matrix. We will use this formula, right? Because X we already know, inputs we already know, output we already know for training data, right? Because here we are doing supervised learning, where we are doing supervised learning. So input output pair we know for all training data points, right? So X matrix we already know, because if we arrange inputs row wise, you will get the X matrix. Y is a vector of output, a vector of actual values, right? So we already know Y values, we already know X values. If you use this formula, you will get unknown vector theta, right? Any doubt here?
When is such a solution feasible or practical?
Yes, yes. But if you want to get this solution, if you want to use this formula, then we must be able to do this inverse operation, because here the solution depends on inverse, right? Because we are inverting a matrix. So matrix inversion is a very difficult job when we have a very large matrix, right? For a small matrix, you can easily invert, but let's say you are having matrix of size millions rows and millions column, then it's not easy to invert that matrix, because matrix inversion is a very costly operation, right? So here, what is the size of this matrix? X transpose X. X transpose X size of this matrix is, because size of X is m cross n plus 1. So size of X transpose is n plus 1 cross m. Size of X is m cross n plus 1. So size of X transpose X is n plus 1 cross n plus 1, right? If you put here the size of X is m cross n plus 1. So X transpose size is n plus 1 cross m. X size is m cross n plus 1. So X transpose X size is n plus 1 cross n plus 1. And here, what is this n? N is the number of feature. So when we have several features in our data, let's say when we have millions of feature or thousands of feature, then we have to invert 1000 cross 1000 size matrix, because X transpose X, size of X transpose X is n plus 1 cross n plus 1, where n is the number of features, right? So if this size of this matrix is huge, or you can say when we have huge number of features in our data, then we will not prefer this solution, right? Because we have to invert this matrix, right? Then we will use iterative solution. But let's say when we only have few features, then we can use this solution, right? Because we will construct matrix X, we will construct this vector Y, and we will use this formula, and directly we will get this solution, right?
Okay. So is it just the number of features or the number of data points overall that also has a bearing on when to use this solution?
Yes, yes. So see, matrix multiplication is not a big issue, right? Only the matrix inversion is, so X transpose very easily we can do. In X transpose, what we will do? We will swap rows with columns, and very easily you can get the X transpose. Again, matrix multiplication very easily we can do. Only we will have problem in this inverse operation, matrix inversion, and the size of this X transpose X is, here is the n plus 1 cross n plus 1, where n is the number of features. So X transpose X depends on number of features and not on the number of data points, right? So for example, let's say uh, you are having three features. You are having three features in your data, right? Assume you are having three features in your data: x1, x2, x3. Now, can you tell me the size of X transpose X? Size of X transpose X will be 4 cross 4, right? 3 plus 1 cross 3 plus, right? Why 3? Because we are having 3 number of features. Now, assume in your data points you are having, let's say, 1 million data points you are having. Even if you have 1 million data points, the size of X transpose X will be 4 cross 4 only, right? So number of data point here is not a problem. Number of feature is the problem, right? Okay.
So
Okay. So
it's not
yes.
clear 100%. If let's say we have got a large matrix, we have got number of rows, then don't we have to inverse every data point as part of the matrix inversion process?
No. So we will construct a matrix X. We will do this transpose operation. Then we will do the matrix multiplication operation. And after doing this matrix multiplication operation, if we have three features, the size of X transpose X will be 4 by 4 only. So we only have to invert a matrix of size 4 by 4. That we very easily we can do, right? But yes, if we are having millions number of data points, there will be million number of rows in X. In X transpose, there will be million number of columns. But once you do this matrix multiplication, we will get a matrix of size 4 by 4 only, right? So we do not have to invert a matrix of million elements. We only have to invert a matrix of size 4 by 4 because there are three features in our input. So size of X transpose X will be 4 by 4 only, right? Any other doubt?
No.
Okay. Okay, now how can you implement this equation mathematically, programmatically? So for that, we will use a NumPy array. So here we are importing NumPy array as NP, and then we are using this random function NP random function of NumPy NP dot random dot rand, and here assume we are having 100 data points, right? Assume we are having 100 data points, and we want to generate these 100 data points. So to generate these 100 data points, what exactly we are doing here? We are generating 100 random numbers, right? Now this command np.random.rand will give you a random number between 0 and 1, right? So if you multiply this random number with 2, you will get a random number between 0 and 2, right? So this function np.random.rand will give you a random number between 0 and 1. And since you are multiplying this number with 2, so now you will get a random number in range of 0 to 2, right? Because originally you are getting random number from 0 to 1. But since you have multiplied this number with 2, so now you will get a random number from range 0 to 2, right? And to produce this type of data, since we are learning here a linear model, so input output relationship must be linear. And to generate this linear relationship, here we will use a equation of line, and we will add some noise to each and every data points, so that we can have uh, points uh, that satisfy a, uh linear relationship approximately, not the exactly, right? So for that, how we are generating data points? Output is equal to 4 plus 3x plus this random number, right? So this output will be y is equal to 4 plus 3x, right? So if we do not use this random number, then all points will be perfectly aligned with the with the straight line y is equal to 4 plus 3x, right? And we do not want that case, because we want some error to be there in linear model. For that, we are adding here some random noises in our data points, right? So as you can see here, if you see these data points, these 100 data points, if you see these 100 data points are satisfying a linear relationship, right? So you can fit a linear model for these 100 data points, right? And these data points are not perfectly aligned along any line. When you fit a linear model, you will get some error, right? Because we have added random noise to each data points, and this random number can be positive, can be negative. So that's why we are having here um, uh, some variations in our data points, right? Okay, so we are generating these data points using this equations y is equal to 4 plus 3x plus random number, right? Okay. So if you plot these points, you will get this type of plot, right? So for plotting, we will use pyplot, plt.plot. We will pass here input values x, output value y, and since we want output points in blue color, so here I'm writing b and then dot. Why I'm using here dot? Because I want this point in dot form, right? So as you can see here, it will output these points in blue dots, right? Okay. So x is the input, y is the output, and output we want to these data points we want to display in dotted blue format, right? Okay. X label we are using x1, y label we are using output y, and x axis ranges is from 0 to 2, y axis ranges is 0 to 15. So I will write here 0 to 2, 0 to 15, and then I will use show command to show this plot, right? Okay. So it will show output data points, and how many output how many data points we are having in our data? 100, because we have generated 100 random numbers, 100 values we have generated, and using 100 random numbers, we are generating 100 data points, right? So we are having 100 x values, we are having 100 random values, and we will have 100 y values, right? So how many points we are having here? 100, right? And this input output relationship is linear, so we can learn a linear model to capture this linear input output relationship, right? Okay. Now we will use this formula, right? Okay. So as I said, we do have bias term in our model theta, and to accommodate that bias term, we will add one value to feature. To input feature, we will add one value, right? So to accommodate bias term, here I am adding a column vector of all ones, right? So I will create matrix X, right? So how can I create this matrix X? By arranging inputs row Y, right? So in matrix X, first row is first input, second row is second input. So likewise, I have arranged all data points in matrix X, and then to accommodate bias term, I will add a column of all ones. So np.c will do nothing but it will concatenate columns of all ones to this input x, right? Now I'm using this formula, right? So theta based means the optimal value of theta is equal to transpose of this x, right? So to do the transpose, I'm using np dot lin algebra dot inverse, right? So using this library, I can do the inverse, right? So xb dot t for transpose, right? Because here what I want x transpose, right? So to do this transpose operation, I'm using dot t. So dot t will do this transpose, right? So xb transpose dot x, right? Because here I'm doing dot product between two matrices, x transpose and x. So here I'm doing dot product between xb transpose and xb, and then I'm doing this inverse operation, right? This inverse operation I'm doing. After inverting, I'm writing here dot product of xb transpose and then dot product with output y, and directly we will get the solution, right? Theta 0 and theta 1. So first value is for the bias and second value is for the slope, right? So any doubt here in this in this program? Right here, why are we adding column vector of all ones? To accommodate bias term, right? So input matrix X we already have. In input matrix X, we have arranged inputs row wise. First row first input, second row second input. Now we will add a column vector of all ones to accommodate bias term, and then we will use this equation to get the solution, right? Okay. So if you use this equation, so you will get this solution where theta 0 is this first value, second value is the slope, right? And this is the original value 4 and 3, right? So theta 0 actual value is 4, slope actual value is 3, and using this equation, I'm getting uh, these values of unknown theta 0 and theta 1. Now, let me ask one question. So, why are we getting 4.14? Why not exactly 4? See, I'm using this equation to get the solution, right? And I'm getting these value as the solutions, right? 4.14, 2.84. But the actual values are 4 and 3. So why we are having here some difference? Why we are not getting the exact values, right? Or what can be the reason for this?
Because of the random noise that we have added.
Yes, because we don't have a perfect linear relationship between input and output, right? Because we have added some random noise to our data, right? Because y is equal to 4 plus 3x is not the relationship between input and output. Because of this random noise, we have introduced some error, right? So that's why we are getting approximate value 4.14, 2.84, right? Because we have added a random noise in our in to generate these data points, right? But yes, if you do not use this random term, and if you use these equations, then you will get the same values. Theta 0 is equal to 4, theta 1 is equal to 3. If you remove this random value, then you will get the exactly same value. Theta 0 is equal to 4, theta 1 is equal to, right? Okay. So we are learning here the optimal weights, and optimal weights are approximately same as the original weights, right? Now, what we will do at the test time? So test time, we will use this optimal value of theta 0. We will use optimal value of theta 0, and we will use equation theta transpose x to get the output, right? Once I know theta hat, once I know optimal value of theta, I will use yes, I will use this equation to make the prediction. Predicted value is equal to theta transpose times input. Output is equal to theta transpose times input. I will use this equation to get the predicted value, right? Now I know the optimal value of theta using these equations, right? I will use this theta value, and I will make the prediction. So suppose in we want to make predictions for two input, right? So this is my first input, and this is my second input. So we are given two input values, and we want the corresponding output value for these two input 1 and input 2. There will be corresponding outputs, right? Now, since we have bias model in our term, so what we will do, we will add one vector of ones to this input, right? So we will add a column vector of 1 to this input x, and then we will use theta transpose x to make the predictions. So we will do dot product between theta and x new to get the predicted output, right? Yes. So in theta, I'm having two values, theta 0 and theta 1, right? So this is my first input. This is my second input, right? So output, sorry. Output is theta transpose input, right? Or you can say the dot product between theta and input, and we will get output. Now this is my first input, second input, right? And we only have one feature, right? So we will construct one matrix. First input is my first row, second input is my second row, right? Because since we only have two inputs, x1, x2, so there will be two rows, and I only have one feature in my inputs, so therefore one column will be there, right? Now what I will do in x new b, to accommodate this bias term, I will add a column of ones, all ones. So 1 1, then first feature of first input, first feature of second input, because I only have one features, right? Now I will use this theta value here, and I will calculate theta transpose x new b, right? So this is my x new b. So size of an output, what I will get? I will get theta 0, theta 1, and I will perform this matrix multiplication, right? So first I will do the theta transpose. So if theta is 2 cross 1, theta transpose will be 1 cross 2, right? So theta transpose will be theta 0 and theta 1. So when I will do this multiplication, I will get the values, right? Sorry. Yes. So this is my first input. This is my second input. So here I will first add 1, right? So I will have here 1 value, and then input x1, right? Then I have this theta value. I will perform dot product between these two. So I will get theta 0 plus theta 1 x1, and the second output will be the theta 0 plus theta 1 x2, right? So this is my output 1, and this is my output 2. So in output I will get a vector of size 2 cross 1, where this first value is the output for first input. Input 1, I am getting this output, and the second value is the output for input 2, right? So I will get two output 1 and output 2. Any doubt here? So why I'm adding here this concatenating this vector of 1, so that I can accommodate this bias term theta 0, right? Because in input I only have one feature x1, right? So this is my first input, second input, right? So I only have one feature in my input. So to accommodate this theta 0 or to perform this dot product between theta and input x, I'm adding here one value to my inputs, right? Okay, so using this program, you can calculate the predicted value. You can make predictions for any given input theta, right? Sorry, for any given input x, right? Okay, the same. Yes. So here we are coding everything by our own, right? So we are implemented this mathematical equations using this program, and then for the predictions again we are first adding one extra feature to our input, and then we are using theta transpose x to make the predictions, right? The same task you can do directly by using libraries, right? So for that, what you will do, you will import linear regression model from scikit.linear model. You will import linear regression, and you will fit your data points to this linear regression model, and then you will use predict function to get the predictions, right? So there are two ways. Either you can implement these equations using program, and then for predictions you will use theta transpose x, and you will get the predictions, or directly you can use library to get the answer, right? So here we are importing linear regression model from scikit.linear model, and using this linear regression model, I am fitting our data, right? So here, what is my x? X is a matrix where we are arranging data points row wise, right? First row, first data point, second row, second data point, similarly, nth row, nth data points, right? And this y is a uh, vector, right? Output vector. So we will fit here input values, we will fit here output values, and we will this linear regression will learn a model, right? Now, if you want to see the intercept and coefficient for this line, you can use dot intercept dot coefficient, right? So you will get the values of M and C, right? You will get the values of bias and slope term, right? So this intercept means the bias term, and coefficient means the slope term, right? Okay. And if you want to make predictions using this linear model, you will use dot predict method. You will pass here the input values, and you will use this model, and you will get the output values, right? Model predicted values in output, right? Any doubt here? Right. So we
This
have seen.
linear regression is internally using the first approach
Yes,
that we discussed.
yes. So this linear regression model will internally use this equation. So what it will do? It will first construct. It will first add vector of one, column vector of all ones, and then it will use. It will use. It will sorry. It will use this equation to get the optimal value of theta, and then it will use theta transpose x or dot product between theta and x input to get the output, right?
Which of these two codes run faster?
No, so both in both ways we are doing the exactly same.
So
So
library doesn't optimize any more than what we have done.
no, in fact, in this code also we are using library function. right? So it's not like that we are doing this inverse operation. So np dot linear algebra dot inverse. Here also we are using library function to get matrix inverse to do this dot product to do this inverse operation. So these functions are already optimized, right? But let's say if you do this transpose operation by your hand, if you do this inverse operation by your own, then that method will be very slow, right? Because then this inverse operation optimization matrix multiplication is not optimized, right? But since we are using this inverse operation, dot operations, transpose operation, matrix multiplication operation from library only, so therefore these functions are already optimized, right? So in linear regression also they use the same function. So that's why in both methods you will get the answer in same time, right? The only difference is if you use this library function, then you don't have to use any equations directly. You will call linear regression model. You will fit data to this linear regression model, and using this predict function, you can make predictions, right? But if you use this first method, then you should you must implement this mathematical equations using this using any programming language, and then you have to use uh, library functions to do this matrix inverse, matrix inversions, right? And then you will get your answer, right? Okay, any other doubt? Right? So for example, what exactly this dot predict function is doing? It is performing dot product between theta and input, right? So theta transpose x, this predict method is doing, right? And this fit function, what exactly this fit function is doing? This fit function is doing nothing but this calculation it is doing, right? This calculation that we have written here, right? Okay, now can you tell me what are the problems with this method, normal method? Some problems I have already discussed. So can we use this method for all types of data points?
Number of features is limited, then we can use this.
Yes, yes. So first important point here is when we have limited number of features, then we can use this method, because we have to calculate the inverse matrix, right? Okay, so this method is since this method is computing an inverse, and this inverse depends on n plus 1 and n into n. So actually it should be n plus 1 into n plus 1, because we do consider bias term, right? Because if we do consider bias term, the size of x transpose x will be n plus 1 cross n plus 1, right? Where n is the number of features. So ideally it should be n plus 1 cross n plus 1, because we are considering here the bias term, right? Okay. So since we have to invert a matrix of size n plus 1 cross n plus 1, where n is the number of features, so therefore if n is large, then uh, it is not practically possible to invert this huge matrix, right? Okay. And since the computational complexity of inverting any matrix is order of n cube, right? So, and yes, even if you use the best optimal method to do this inverse operation, the size complexity is order of n power 2.4. So this is the best possible time complexity uh, for matrix inversion case, right? But we generally do not use this case, because this method involves recursion, right? Several recursion it uses, and it's theoretical bound, right? But when you use this method practically, one hidden constant is there, right? So roughly you can think here the matrix inversion operation is very costly, right? And let's say when you increase n, so suppose let's say if you increase from number of feature from n to 2n, if you double the number of features, Here, if you put 2n, the time complexity will become 8 times, right? If you put here 2n in place of n, what you will get? 2 cube. 2 cube extra you will get. So 2 cube is 8. So now time will become 8 times, right? So if you double number of feature, the time will increase 8 times, right? So this method is very slow when we have huge number of features, right?
Does it also lead to overfitting?
No. Here,
Closed form solutions?
yes. So for that, what we can do, we can use regularization, right? So regularization I have not covered, but yes, overfitting problem may be there in this normal solution as well as in iterative method. Also, we may have the um, overfitting solutions, right? So it's not because of this mathematical equation. Overfitting we may get because we are not using here any regularization term. We are directly optimizing this loss functions, so that may cause a overfitting problem, right? Now this overfitting, so since here in both method, in normal in equation method or in iterative method, we are only minimizing loss function, so overfitting may be there in both of these solutions, in closed form and iterative. And how can we prevent overfitting? If you, let's say, if you want to prevent overfitting in closed form solution or in iterative, we will add one more term here, and then term is called the regularization term, that I will discuss later, right? So we will add one more term here, regularization term, that will fix overfitting problem in both of these solutions. In normal form also it will solve the overfitting problem, in gradient descent also it will fix the problem, right? Yes. So this method gets very slow when we have when feature grows large. When we have huge number of features, then we will not use this method, right? But this method, linear equation, uh, so yes, so this normal equation is linear with regards to the number of instances in the training set, right? So time, this inverse time will become 8 times when we double the number of features, right? When we increase this n value, when we increase, so let's say when we double this n value, the time will become now 8 times, right? So this method time is not linear with respect to number of feature, and in fact, when you double number of feature, it will become 8 times, right? But this method is linear with respect to the number of training set. The only problem is you must be able to fit all points, training data points in memory, right? So here the memory is the problem. So suppose, let's say, if you have millions of points, but let's say that millions of points you can very easily fit in the main memory, then you can calculate, you can use these equations, right? Because here we are doing this matrix multiplication, then we are using this transpose operation, and then we are again doing the matrix multiplication. So if you want to do this matrix multiplication, this matrix X and matrix Y has to be in the main memory. Or let's say this X transpose, if you want to perform this matrix multiplication between X transpose and X transpose and X, you must load in the main memory, then only you can do this multiplications, right? So if you are able to do this matrix multiplications, then no problem, right? But let's say if you are having millions or let's say billions of data points, and then now you cannot load X transpose X in main memory, then this method will create a problem, right? So number of instances or number of examples or number of data points is not a problem if you are able to load these matrices in the memory, right? But let's say if you have the limited memory, you cannot load X transpose in memory, then yes, in that case also you cannot use this method, right? So one problem is when we have huge number of features. The other problem is when we have limited memory and we have uh, uh, when we have millions or billions of data points in our data set, right? Then also this method may create a problem, because to use this method we need to calculate transpose, we need to perform matrix multiplication, and for that we need to load these matrices into memory. Then only we can do this type of calculations, right? Okay. So memory, if you have the limited memory, then this method may create a problem, right? Because if now in this case you have millions of data points, then you cannot load these matrices into limited memory, right? So what
Isn't there
we will
a way that we need not load this entire matrix in memory? We can bring in some data points in memory and the rest can be kept on disk.
yes. So in fact there exists methods using which we can perform matrix multiplication even if we are not loading matrices completely. But again uh, with those methods we are having some limitations, right? So yes, so because even if you are loading matrices partially to do matrix multiplication, let's say if you have huge number of data points, then it may possible that even that partial matrix you are not able to load, right? Then we cannot use this method. So for that, what we will use? We will use iterative methods, right? Because there are two problems with this method. The number of features, because we have to invert a matrix of size feature plus 1 cross feature plus 1, number of feature plus 1, right? N plus 1 cross n plus 1. The other problem is if we want to use this equation, we need to load these matrices into memory. So we must have sufficient memory to load these matrices in memory, right? So time and space is the problem, right? But yes, if you have only 1,000 data points, if you have let's say hundreds of features, then you can use this method very easily, right? Okay. So linear so we will explore different ways to train a linear regression model which are better suited for cases when there are large number of features. Even if we have millions of features, then also we can learn a linear model, right, using iterative methods. Or let's say if we have
Question
too
here,
many training. Yes.
is closed form solution is a better solution if memory is not an issue?
No. In closed form solution, we will have, you can think like we will have one formula. So using that formula directly, we can get the answer, right? But it's not like that for every problem. We will have a formula, right? In this case, for this problem, for this linear regression problem, we are lucky that we end up getting the closed form solution, right? And
So wherever
how?
we have a solution available, does it perform better than the gradient ones?
No. The other one, the iterative one, will give us uh, the solution using several iterations. And the other problem is we may get the optimal solution, we may not get the optimal solution, because in iterative methods there are lots of we will use several hyperparameters, right? If we are not tuning hyperparameters properly, then we end up getting the suboptimal result. But if you use this equation, you will always get the best possible answer, right?
So can we say it's the preferred solution if the number of features is less and memory is not an issue?
Yes, you can say, but again, the problem has to be the convex,
Okay.
right? So see, what is the form of this loss function? Form of this loss function is something like x square, right? So if the form of equation is loss function is convex, in convex case we will get the global solution, right? As you can see, let's say suppose you are optimizing this type of function. Now here we are having several solutions. So for example, this is also a valid solution. This is also a valid solution, but this is the best solution, global solution. So when we have several local solution and global solution, sometimes we end up getting local solution. Sometimes we can get this global solution. So if you use the iterative method, then we may get global solution rarely, because there are lots of hyperparameters that we need to tune in iterative methods. So we end up landing local solutions if you use the iterative method, right? And it also depends on what type of function we are optimizing. So suppose if you are optimizing a convex function. Convex function means function looks like a cup, right? And the negative of convex function is a concave function. So concave function means inverted cup. So if you are minimizing a convex function or maximizing a concave function, then as you can see here, we only have one local solution, and that solution is a global solution, right? Here also, let's say if you are maximizing something, then we will exactly have one solution for maximizing this function. For convex function, we will have exactly one solution, and that solution is a global solution, right? So it depends on what type of function we are uh, optimizing. So even if you are using iterative method, and if you are tuning hyperparameter appropriately, then achieving global solution is also possible in iterative method, right? Because here using iterative method, very easily you can get this solution, because we only have one solution in this case, right? And that solution is a global solution. But let's say when we have several solution possible, so for example here, this solution also is possible, right? This is also a solution, but since it is a local solution, again local solution, and this is the global solution, then it may possible using iterative method that you end up landing with the solution, right? The solution is a valid solution, because here also this value is minimum if you consider this local neighborhood, right? If you consider this local neighborhood, this is a valid solution, but the solution is not a global solution, it is a local solution, right? Any other doubt? Okay, so next session I will discuss iterative approach, and gradient descent is an iterative approach where we will use several iterations to get the solution, right? But again, here in this approach, we will have several hyperparameters, and we have to tune these hyperparameters to get the solution, right?
One quick question. Next week we have a test on linear regression. So for that, is everything in this slide included, or is it till what we have covered so far?
Yes, yes. So next
Because I don't
week,
think we'll be
I
able
think
to.
yes, yes. So I think 9th of November, I will finish this training model topic completely, right?
Okay.
Yes.
So
So in syllabus, only linear regression is there, or because there are several topics in this in training models, right? So linear regression is there, then gradient descent, iterative method is there, and then this polynomial
yeah, I mean,
regression is
I
there.
don't know the
Mm.
yeah, I mean, all this is there, But in terms of exam, the exam says only linear regression. So we believe that all these will be there. But if
Yes, yes.
we are
So
going to cover
linear
it,
regression, yes, yes, linear regression I will finish in, in tomorrow session, right? And then we will start topics like polynomial regression, right? And then we will see learning curves, right? Because training model, this PPT contains several topics, right? Learning curve is there, then
okay. So
regularization is also there.
okay, so for the exam, linear regression and gradient descent, all four will be included, right?
Yes. So tomorrow I will tomorrow session I will cover iterative approach, gradient descent. In gradient descent, we will mainly see these three approaches: batch, stochastic, and mini batch. And all these three are nothing but the variant of gradient descent method, right?
Okay.
All four means what? Linear regression and gradient descent, these two, right?
Yes. So linear regression, for to solve this linear regression, we are using two types of methods. First one is this closed form equation, and the second one is the gradient descent. In this gradient descent, there are three more variants. So I will discuss three variants of gradient descent. So in total, there are four methods. First is the closed form solution, and the three methods we have for iterative approaches, right?
Can you please put this PPT on chat?
Yes,
It is
yes.
not already.
I think I have already shared PDF file. Okay, so let me share it again. Yes, so please download. I've uploaded PDF file. Yes, so some PPT file is also there, but that file is not required, right? Only this PDF file you can refer. This PDF file and the IPython Jupyter notebook file, right?
Do we, again, as part of the syllabus, do we need to know anything about calculus or anything which is not in the
No.
slide should not?
Calculus, actually, this calculus part is not required. Here, I'm using this calculus slide so that you can get a clear idea what exactly we are doing, right?
Okay.
So if
Thank
you
you.
want, I can also share these slides. So tomorrow I will share all slides, but only this PDF file and the IPython Jupyter notebook file is the main content, and the other slides
Okay.
I'm using just for you so that you can get the better idea, right?
Yeah. Thanks a lot.